All right, it's time to get started. We have a very interesting topic to cover at the start of today's class that maybe some of you have heard of before, and maybe it's completely brand new. I'm guessing it's completely brand new to most of you. That concept is non-determinism. Who has run into the concept of non-determinism in some class before? I'm always curious, for those who have seen non-determinism, since this is a really hit or miss topic, I've heard it explained really well, and I've heard it explained in a way that makes me want to stop being conscious. So, for those of you who have experienced non-determinism before, what is your understanding of it, or how do you choose to understand it? Because I'm also always looking for new ways to explain a topic. So I'll ask you before I talk you through the way that I understand non-determinism. All right, I'll bias you with how I think of non-determinism. So every program you have ever written is deterministic. The way that you have thought to solve a problem has probably been deterministic. What that means is you are going to use some kind of algorithm and you are going to hunt for a solution to something. So the example that I like to use is cracking a password. Let's say that there's a password that you want to crack that is, you happen to know that it is 6 or fewer characters. And it can either be, any of those characters can be uppercase letters, lowercase letters, or digits, no symbols. How long would it take you to do that? How many guesses would you need in order to, in the worst case, know that you have figured out the password? There are 26 plus 26 plus 10 possibilities at each character. And there are 6 of them, and they're all independent of each other. So you would have 62 to the 6th possibilities that you need to go through and check, and that's just for things that are of size 6. So you need to add to that 72 to the 5th for everything that's of size 5, 62 to the 4th for everything that's of size 4, all the way down to 62 to the 1st for all of the single character passwords, because those are so secure. But the idea is that is a lot. It's not as many for a computer that can do millions of these per second, but it's still a lot. And of course, the longer your password is, that scales exponentially with the difficulty of cracking that password. Non-determinism, on the other hand, says whenever you have a choice, you're going to choose the right one. Without having to search for what the right character is, you're just going to decide or choose whatever the correct one happens to be. Another way to think about that is it's a verification algorithm. So when I tell you that my 6-character password is Kane ! Even though I said symbols weren't allowed. Kane 11, I don't know, doesn't really matter what it is. How long would it take you to verify yes or no that is my password? It's proportional directly to the length of the password. We've removed this concept of exponentiation from the search space, and now you just have a linear algorithm, a linear verification algorithm. So this is an example of a problem that, if you want to solve it deterministically, takes exponential time. And if you want to solve it non-deterministically, takes linear time. Does that concept make sense to people? So the brute force way of trying every possibility until you happen upon it, or a verification where you know what it is and the answer is yes or no. Is that the correct answer, yes or no? So to explain this in a bit of slide detail, when you have a deterministic algorithm, each step is uniquely determined by its current state. There's no potential branching factor. So as I mentioned, every program you've ever written is deterministic because we don't really have a way of writing non-deterministic algorithms, at least that search a space, without being told what the answer is and then verifying it. So this is the same example that I just gave you. Write a program guarantees that you crack a password of 6 characters through brute force. Takes a lot of attempts. In non-determinism, you have a set of possible next actions from the current action. So in this case, we would have 62 possible next characters to enter. And of those, we're just going to choose the right one. So rather than doing an exploration of each possible successor state, we assume that the correct next state is going to be automatically selected. So this is how I view non-determinism. And I think that a combination of those kind of 2 ways of understanding of it, of a verification algorithm, or just knowing what to do next whenever there's a choice, either one of those will work as far as understanding this concept of non-determinism. Now, we see this in a lot of different places in computer science. How many people have taken algorithms? I think it's a prerequisite for the course, so it should be everybody. In your algorithms course, did you talk about NP-complete algorithms? Yeah? One person? Raise your hand if you talked about NP-complete algorithms in algorithms. NP-complete is a class of algorithms that, if you're trying to brute force them deterministically, take exponential time. And if you want to non-deterministically solve the problem, it takes some kind of polynomial time. So that could be linear, quadratic, n-cubed, cubic, quartic, quintic. What we haven't shown, and is a completely open problem in computer science, if you solve this, you're an instant millionaire, is in this class of algorithms, solve any one of them deterministically in polynomial time. We have no proof whether or not any algorithm in this class can or cannot be solved deterministically in polynomial time. Very hard proof. Many people have been trying for decades. But for the scope of this class, how we're going to use non-determinism is in the construction and understanding of non-deterministic state machines. We put some pretty hefty requirements on DFAs when we talked about DFAs. So it had to be a total function, meaning that at every state, we needed to have an output edge for every symbol in the alphabet. And every time we make a transition, we had to consume a character out of the input. We're going to see that we're going to relax a couple of those constraints when we construct NFAs. So it looks very similar to a DFA's formal definition. It's still a quintuple, and the quintuple still has the same symbols in it. It's defined exactly the same way, except for one change, which is the possible transitions. The possible transitions in a DFA were, we had the possible number of states in the DFA times or cross the number of characters in the alphabet. If you were in Q0 and the alphabet was AB, there were going to be 2 and exactly 2 edges out of that led to some other states. It could be the same state, could be some other state, but it always had to be exactly 2. Now we're going to redefine this possibility to include every character in the alphabet union Lambda, union consuming no symbols. And that leads us to have 2 to the number of total number of states in the NFA, possible transitions from in the entire thing, which is wild. It's exponential. It can grow to be significantly more complex, but it's also logically easier to construct when you have fewer constraints on that construction. So let's talk about the 2 major differences between DFAs and NFAs. The first one is that lambda transition. We're going to define that lambda transition as a transition between 2 states in the NFA that do not consume an input character. So now we have the ability to move around from state to state without moving the input to the right and consuming a character. So we can just teleport. That's the way that I like to think about it. We can just move from state to state, teleporting. So we no longer have a longest possible path. If we're trying to determine whether or not a string of length 5 is in a language, in a DFA, we would know within 5 transitions. In an NFA, we have no such guarantee. You can also have multiple different transitions out of one state consuming the same input character. So you could go from Q0 to Q0 consuming an A, or from Q0 to Q1 consuming an A, or Q0 to Q2 consuming an A. Before, there was only one possible transition that you could have that consumed that input character. Because that creates an immense space, if you forced this to be the same kind of total function that you had with a DFA, you might be making a ton of edges. So there is one other change that we allow that is saying that you do not have to specify every possible transition out of a state. If it leads to a trap state or a failure state, you no longer have to specify that. If there is no possible transition at that point, we reject the string. Questions about this definition before I give you an example of what one might look like? All right, looks very much like a DFA. It has the same nodes and transitions on edges, but we will notice some oddities. Where do we see any of these numbered differences on the top of the slide embedded within this diagram at the bottom? Yeah, there's absolutely no transition out of Q2. So if we get to Q2, it's a trap state. We cannot consume characters from Q2. So if there are further characters left in the string and we find ourselves in Q2, we reject.
Lambda transition.
Lambda transition between Q0 and Q2. Absolutely. That means that we can just teleport from Q0 to Q2 without consuming any input. What else?
I don't know if I'm correct here, but from Q1, you can have a 0 and go to Q2, but you can also go back to Q2.
Yeah, exactly. So we can consume a 0, and we have a choice if we're in Q1 of going to Q0 or Q2. So what are we thinking with regards to NFAs? How could this potentially be useful or applied, or what are you thinking with regards to this? There may be, like, for instance, multiple paths through. Yeah.
I don't know, like you're just trying to make sense out of something that's like kind of nonsensical. Like that's what it seems.
Sure. We'll find ways that we'll notice that these are easier to construct than DFAs because there are fewer constraints. And one of the next places we're going to go is showing that whenever you construct an NFA, you can construct an equivalent DFA. So if you can construct an NFA to solve a problem, it is a regular language and you can convert it to a DFA. So whenever you could construct, if I say, for instance, construct a DFA for this, instead you could construct an NFA and then go through a precise algorithm that converts the NFA that you constructed into a DFA. And that will be the DFA construction process rather than you're having to adhere to the DFA's precise constraints.
This might be a dumb question, but why would you do that? Instead of just making the DFA?
Some languages are going to be really difficult to construct DFAs for. I haven't given too many examples of that yet, but there are some languages that are very, very, very precise. Like, so instead of an even number of A's, it could be the language parentheses AB star AAB plus, which is the closure minus 0 possibilities. You can imagine there's a very, very precise language of certain kinds of repetition in certain places that would make constructing a DFA really tedious and a ton of states. And you will find that, in fact, you can usually construct the same NFA for a DFA with significantly fewer states, which means that it's much easier to grasp and to come up with a solution for. And we'll find that when we go through that translation process into a DFA, this will explode in size and we'll come up with a DFA with significantly more states, but it will always be possible to do so. So that's one of the reasons we study NFAs.
So when you have something like this, where you're in Q1 potentially, and you can go multiple directions when reading a 0, is the decision on which way you go random, or is it based on context and memory?
Basically, it's non-deterministic. If there exists a path to a final state consuming that string, we will accept. Even if 9 out of 10 possible paths reject, if there is a path that accepts, we accept. So you'll notice that, for instance, like Q2 is a trap state and Q0 is a final state. So the string 1, 0, 1, you have to be here, although you could land a transition here and reject immediately. But you go 1 here and then 0, you have a choice between a trap state and a final state. So 1, 0 would be accepted in this language because there exists a path to a final state, which is why we use non-determinism. Whenever there's a choice, we're just going to pick the one that's going to lead us to a final state if such a path exists. The only time we'll reject is if it is not possible to reach a final state.
What's the point of putting the 0 from Q1 to Q2?
Oh, this is a total bullshit. It serves no purpose. But yeah, you're absolutely right that you have the full power to be able to construct this. This was just as simple a thing as you could put together to be able to get all of those differences in the same diagram. Yeah, it does not have any meaning. So the first time you hear and see non-determinism, you think this is a really theoretical concept. It seems like it has no application whatsoever. And why do I bother to know this? So lots of reasons. So many problems have much easier non-deterministic solutions than deterministic. So being able to come up with a non-deterministic solution can be significantly easier, but only if that non-deterministic solution has value. So the value to a non-deterministic finite acceptor is that you can convert it into a deterministic finite acceptor. If there was no conversion algorithm between the two, then an NFA wouldn't really serve us any value. Another possible example is search and backtrack algorithms. If you've seen these in an algorithms class, where you're doing some kind of depth first search, something like that, where you search as deep into it as you can, and if you run into a dead end, then you backtrack and you continue to do this until you find a goal or figure out what you were trying to do and find that. Think about optimizing a search and backtrack algorithm. How can you find the goal faster? If you're able to make a choice that is most likely to lead to the goal, if you have any information about a bunch of different decisions, rather than just always exploring the left child and then the right child, if it's a binary tree, then you would be able to take in some information and decide what is more likely to lead to the goal. So if a particular path leads to failure, backtrack, look at the next most likely choice. If you look at non-determinism, this most likely choice is going to be some kind of multiple of the non-deterministic complexity as compared to the deterministic complexity. If, for instance, we have 10 choices and we know that on average, it's going to take us 2 guesses to find the correct path of that, then we're going to scale better based off of the non-deterministic approach than we will off the deterministic approach. So it serves us a little bit better than just straight worst case analysis like you might have seen in data structures or algorithms. There are certainly many times and places for worst case analysis, but oftentimes average case analysis is really difficult, but having an understanding of non-determinism may help you to have more tools to better approximate an average case analysis for an algorithm. I also talked about this already. P equals NP is an algorithm that is non-deterministically polynomial, deterministically polynomial. Is that true? NP complete algorithms is a class of algorithms that are non-deterministically polynomial, but deterministically exponential. Has anyone heard of the traveling salesman problem? That's probably the most commonly heard NP complete algorithm. Yeah. So the traveling salesman problem says that you have a graph, and the graph represents nodes or cities, or vertices or cities, and edges between them are distances between them. What is the shortest possible path from starting from a particular node and visiting every other node in the graph, returning to the city that you started in? That's really simple if you have 3 or 4 or 5 nodes in the graph. But as this scales to 1,000 nodes, 1 million nodes, it starts getting completely unwieldy. Trying to figure out what that shortest path is going to be exponential in the scope of the number of nodes and edges in the graph. But imagine that someone told you and said, this is the fastest path on this graph. How long would it take you to verify that? From every node, you could look at every other potential edge leading somewhere else, and you would only have a limited, fairly linear amount of work to do based on the number of edges in the entire graph to figure out, is there a better path than the path that was given to me? So that's how it is non-deterministically polynomial. If someone gives you a solution to it, then you can verify that solution quickly. But coming up with that solution is a tremendous amount of work. Questions on this concept? So no proof exists one way or the other. Is P equal to NP? Yes or no? If you can come up with it and it's mathematically sound, you are rich. We've been trying for decades. Grammars sort of have a built-in non-determinism to them, and we'll talk about this when we talk about regular grammars and context-free grammars later in the course. But they have some built-in non-determinism whenever you have that bar exclusive or that says that you can pick one or the other way of representing a particular production. If you're using a particular production, you have a choice between the left-hand side or the right-hand side for how you're going to expand that production. Then we have that built-in non-determinism where you could do one or the other. And the question is, can we construct the query string from this grammar? All right, so let's start getting you involved a bit. So let's design some NFAs for some languages. Note that you can have a language that is composed of sublanguages using a union like this. So the language is A to the n with n greater than or equal to 3. So strings that have 3 or more A's in a row. Union ABA to the n is greater than 1. Note that the exponent here is just attached to this A, not the whole thing. If it were attached to the whole thing, there would need to be parentheses around the whole thing.
You know, the union here, is that like, it would have to start with 3 or more A's and then do the ABA, or is it just, it needs?
It's an or, basically.
Or.
Think of it as an inclusive or. So if you had a string that started with 3 n's, great, you're done. It's in the language. If you have ABA, it's in the language. ABAA, it's in the language. ABAAA, it's in the language. So yeah, it's an or. It can be one or the other or both.
And so with non-deterministic, we don't have this in some cases like trap states, because if it just can't find a path, it just.
Correct. Yep, you only need to put what will help lead you to a final state. Which makes these significantly easier to construct. If you have a solution to this as an NFA, try to make a DFA for it. And maybe that will help convince you that constructing an NFA for languages is significantly easier than constructing a DFA.
That's it. Yeah. That's all. Just do what you want.
Do we buy it? This solves the first half of the union?
Yeah.
We just need to see, we need our string to start with 3 or more A's. And that is A to the n is greater than or equal to 3. Now, what non-determinism is going to allow us to do with this union, since this also starts with an A, is be able to make a second state out of the start state that also consumes an A. Not at all illegal in a DFA, cannot do it. Perfectly fine. And then we read a B. Here we go to Q5. And we read an A. And it can be A to the n. You don't even need a new state here. You can even transition this up there. On an A. It does not need to be a total function. So we can just stop here. From this, just go there.
Or from, yeah, Q1 down to.
Yeah, down Q1 to Q5. You could do that. Sure.
What stops you from just saying going from Q1 to Q2, you have A or B?
Yeah, we could do that too.
And you just don't need the bottom half.
Yeah. So my point is that you can construct this precisely based off the definition of the language. You can start to make shortcuts as you do that to minimize the number of states. You can, it's very easy to do. Yeah.
So what happens is you have an input that isn't something or you inputs there it is, same state.
It'll just immediately fail.
Oh, I mean,
Yeah, like for instance, if the very first character is a B, there's no transition defined out of the start state for that. So there's no reason to continue parsing the string, immediately fail, it's not in the language.
Okay.
Which, if you look at the language definition, nothing that's in the language starts with a B. So an NFA allows us for an early failure, which is nice.
Do you even need the loop on the A? At
Here,
that point, you know it's accepted, correct?
in order to accept, we need to get to the end of a string. Because otherwise we could stop early as soon as we get to any final state.
Okay.
And that isn't necessarily the case. If there's no way to get back to that state by the time we finish consuming characters. So we can't consume early unless, or stop early unless we reject.
Okay.
So that one's actually not too bad to construct a DFA for. Let's try another one. A to the n is odd, union ABB to the n.
I mean, that's what we're doing, so this.
Yeah.
You just have to say you have to start.
No, no, you're right.
You know.
You're right, you're right.
We're saying the same thing. So it has- See what the-
That was my first thought.
So you have as many of these.
But then what if you have a rate? C. You know, like what prevents that and having
Yeah.
multiple
Yeah.
A's and then.
Greater or equal to.
It's gonna start with the.
Just
Yeah.
have it.
Yeah.
Yeah, that's a good point. Does this work? That's the reason I drew this, is if you do just the left-hand side and just the right-hand side, you can combine them into some instances where you might not want to accept them. So an example of this is A, B, B, B. We accept that string according to this NFA. Yes. Should we? No. So this is an instance where trying to minimize the number of states and combine the different unions might lead us astray. So it's often best to just leave them as their own separate pieces. So we did the left side of the union here. We can also turn it into an NFA or keep it an NFA by making multiple possible transitions out of the base. And we'll do that, lead to, we'll make this Q2, then B, Q3, and loop the B. More states than the other one, but now we can't have that weird combination of something like A, B. In this NFA, we will not accept that string. Yeah, we will. We still will, because we allow this to go back. So we need a separate one out here that loops back. Now that's yeah.
If I have a final state, but then I read something that read like B, or I guess A. Would that end the? It's not the nation. True or false?
So give me an example based on this, say like something like string AB.
Yes, A, B. So I'm not sure that needs to be read out.
So we have, if we're gonna look at this deterministically, we have to parse every possible path through this NFA that ABBA could take. So one of them reads from Q0 and transitions to Q1, then sees a B and can't do it, so it fails. So we have to think about this path. Going down this path, A, B, B, there's no way to get to an A from here, from this final state, so we will also fail on this path. So there are two possible paths through the NFA, both of which lead to failure. So because of that, this string is not in this language. Which makes sense if you try to pair it to either one of these definitions, and you'll find that it doesn't make sense according to this diagram or this logic. And that you can use exactly, this is a very good string for that, because it can help tell you whether or not this diagram is correct. Yeah, excellent observation. Other questions on this? All right, we're gonna spend the last few minutes going through the tedium that is converting NFAs to DFAs. It's not fun. But it's really important to know how to do, because constructing NFAs is much easier than constructing DFAs. So as long as you know the process here, you can make an NFA and then go through this algorithm to convert the NFA to a DFA. So things to note going into it, a DFA is a restricted NFA. That makes sense. It's an NFA, but there are some additional restrictions on the rules of constructing the NFA. So think about a particular DFA and think about how many NFAs you could construct that represent that particular DFA. Think about the logical converse. Remember the concept of converse from discrete math? If the statement is A implies B, then the converse is B implies A. So a DFA has many possible NFAs. Does an NFA have many possible DFAs? Correct. There is exactly one DFA for any particular NFA. So you can basically think of it as there's some DFA and there are a bunch of possible NFAs. For that DFA. Which means that if we're able to construct one of these, which is easier because there are so many of them, if we can map an algorithm that did this conversion, then we don't have to hunt for this. We can find any one of these and apply the same algorithm to get here. Think in advance. Try to figure out the logic behind this algorithm. I like to always do this before revealing an algorithm because critical thinking is cool and someday someone might come up with it again without seeing it for the first time. What rules would you need to have in place in the DFA that's constructed from any given NFA to be able to do that process in the abstract? What would a state in the resulting DFA represent? Yeah,
I mean, just one thing that comes to mind, if you're ever at a state in an NFA where you have a certain next character or whatever that isn't represented, you would just lead to a trap state.
Sure. So the construction of trap states based off of that. Sure. It turns out that if we're going to construct a DFA from this, all of the DFA states are going to be some subset of the possibilities of the states that you could be in an NFA. So let's say we have an NFA with 3 states. Q0. I'll do it this way, a little bit better for how we read. The transitions between this aren't important for the moment. But if we were to convert this into a DFA, we would need there to be a state representing Q0, a state representing Q1, a state representing Q2, a state representing either being in Q0 or Q1, Q0 or Q2, Q0 or Q1 or Q2. If we came up with all of these states, then we could say on a particular input, let's say that we from Q0 can read an A or read an A. Then this would be a transition from Q0 to the state that I didn't write, Q1, Q2. Because you could be in either Q1 or Q2. So this state representation in the DFA would have a single transition consuming an A. So that's why I say an NFA with very few states will explode into a DFA with a lot more states. But those states represent some combination of states that you could reach following the rules of an NFA. Does that concept make sense? So you're converting multiple different transitions down into a single transition, but blowing up the number of states as you do so. So that's kind of the intuition behind it, and I think if you have that intuition, then reading the algorithm makes a lot more sense. So thinking about everything that's currently on the board. You have an NFA, you're gonna start adding states to the NFA, representing all possible combinations of states that you could be in. And then slowly removing the restrictions or making it more restrictive to be a DFA from an NFA with those states. Does that whole process result in a DFA intuitively? Does that allow you to move or remove the concept of reading the same input character and adding and being in different states? Does that allow for lambda transitions? Does it remove lambda transitions from an NFA? The answer is yes. If you do that, you're able to remove all of those and further restrict it to be a DFA. Number of states in the associated DFA is 2 to the number of states in the NFA, which is kind of gross to think about. So I'll leave you with this example. We only have a couple minutes, so try to get started on that process of what does it look like. We have very few states. 2 to the 3 is going to be 8 possible DFA states. Think about and start working through what is it like to construct this DFA from this 3-state NFA. Things that will help you get started. The initial state will stay the same. So if the initial state in the NFA is Q0, the initial state in the DFA will also be Q0, not Q0, Q1 or Q0, Q2, but that would be the case if there was a lambda transition from Q0. So any state that you could be in without consuming any characters, that's going to be the initial state in the DFA. And this will help you with your first transition in the DFA. You're unfortunately out of time. But this will be a very good exercise to work on over the weekend. Focus on homework first, but if you have some extra time and energy, see if you can give this a best attempt. And we will come back on Monday and walk through the construction of the solution. Have a good weekend. Don't freeze to death.
I decided to get that one.